Anyway, this lecture will answer two questions. In the first question, we find out the size of this angle APC is equals to x, so we have to find out the value of this angle x. In the second question, we find out the length of this line segment CD is equals to x. So we have to find out the length of line segment x is equals to CD. So we start with the first question. In the drawing, we have the angle ABC. This is angle ABC. Is equals to 15 degrees in size. This is angle ACB. Is equals to 30 degrees in size. We also know that BP, line segment BP equals to line segment PC. So we define the length of line segment BPSA. Then the length of line segment PC must be also equal to A because they are equal to each other. In the next step, we'll do a construction, that is to say, we'll extend side AC of this line ABC by side line. In the next step, we will do another construction. That is to say, at this point B, we will create angle that will be equal to 15 degrees in size in the following way. BA will be one leg of the angle, and the other leg will be created in such a way that it will create 90 degrees with the leg BA. So this angle equals to 15 degrees in size according to our construction. In the next step, we'll extend this leg by side line until it touches the extended side CA. And we will define the touching point of the extended leg with this extended side CA. This point is point M. But during all those constructions, we created the associated triangle BMC. Triangle BMC is an associated triangle because of the fact that those two angles are equal to each other. Each of them is equal to 30 degrees and therefore they are equal to each other. So triangle BMC is an associated triangle, therefore we can implement here rule 20. Repeat click on rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the domain, we have the associated triangle ABC. Triangle ABC is an associated triangle because of the fact that AB equals to AC. BC is of course the base of this associated triangle ABC. According to this rule 20, the perpendicular AD to the base BC bisect the base BC. First of all, those triangles are both equal to 90 degrees because AD is the perpendicular to the base BC. So according to this rule 20, the perpendicular AD bisects the base BC. That is to say, the perpendicular AD divides the base BC into two halves. The first half is BD, and it is of course equal to the second half DC, and each half equals to BC over 2 because of the fact that BC has been bisected by the perpendicular AD. So BC equals to DC equals to BC over 2. Again, BD equals to DC equals to BC over 2. So we can implement rule 20 in our domain. I put in our domain BC is the base of this associated triangle, again triangle BMC. So according to rule 20, the perpendicular from point M to the base BC bisect the base BC. Well, the perpendicular from point M will touch the base BC. The perpendicular from point M must touch the base BC at point P. Why? Because of the fact that point P is the midpoint of the base BC. Why point P is the midpoint of the base BC? Because at point P, the base BC has been bisected into two halves. The first half is BP is equal to A, and this is equals to the second half BC, this is also equals to A. Therefore, the perpendicular from point M to the base BC must touch the base BC at point P, not at any other point. Because of the fact that the perpendicular MP bisects the base BC. And point P, and the base BC has been bisected. This is the midpoint of the base BC. So actually, this angle equals to 90 degrees in size. This angle also equals to 90 degrees in size according to our construction. And P is perpendicular to BC. Therefore, those two angles must be equal to 90 degrees in their sizes. This is the right triangle BMP. This right triangle BMP. It is very easy to see that sin 30 degrees equals to MP over MB. And again, in this right triangle BMC, BMP, sin 30 degrees equals to MP over MB. We define the ref of the hypotenuse MB as 2B. And therefore, sin 30 degrees equals to MP over MB. MB equals to 2B according to normal definition. Sin 30 degrees is 1/2, so 1/2 equals to MP over 2B. Here we will multiply this equation by 2B. You get that 2B over 2 equals to MP. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled, and we have only with B here. So if you found out that MP equals to B. This is the perpendicular MP to the base BC. It is equal to B units in its length. Therefore, we found out that if MB equals to 2B, then MP must be equal to B. The next step, we will focus on this big associated triangle MBC. In the big associated triangle MBC, line segment AB is the angle bisector of angle MBC. Why? Because AB bisect angle MBC into two halves, each half equals to 15 degrees in size. And because of the fact that AB is the angle bisector of the associated triangle MBP, we can implement here angle bisector theorem. Angle bisector theorem that is also defined as rule 19. So repeat quickly on rule 19. According to rule 19, it is also defined as angle bisector theorem. First of all, we know that this is triangle ABC, and we know also that AD is the angle bisector of triangle ABC. Why AD is the angle bisector of angle BAC? Because it divides angle BAC into two halves, each half equals to theta. And because of the fact that AD is the angle bisector of triangle ABC, the angle bisector AD divides the sides of triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. Again, BD over DC equals to AB over AC. So we can say that angle bisector AD divides the sides of this triangle ABC proportionally. So we can actually implement angle bisector theorem. This rule 19 in our drawing. Why? Because in our drawing, this is the associated triangle MBC. AB is the angle bisector of this associated triangle MBC. So according to angle bisector theorem, because of the fact that AB is the angle bisector of triangle MBC, angle bisector AB divides the sides of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Again, MB over BC equals to MA over AC. So write it down. The right triangle, the associated triangle MBC, we know that line segment AB, LS is the abbreviation for line segment. Line segment AB divides the sides of the associated triangle MBC proportionally. Therefore, according to angle bisector theorem, is also defined as rule 19. Angle bisector AB divides this angle MBC into 2 halves, and therefore, according to angle bisector theorem, angle bisector AB divides the size of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Therefore, MB over BC equals to MA over AC. MB over BC equals to MA over AC. MB equals to 2B over BC. BC equals to A plus A, that is 2A, and it equals to MA over AC. So total, according to angle bisector theorem, this is also defined as rule 19. We have found out that 2B over 2A equals to MA over AC. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled, and we have only here with B over A. B over A equals to MA over AC. And again, we should find out that B over A equals to MA over AC. In the next step, we'll focus on this right triangle, triangle MPC. In the right triangle MPC, line segment AP this is line segment AP divides the size of this triangle MPC proportionally. That is to say, B over A equals to MA over AC. And again, when we found out that B over A equals to MA over AC. So it is known in the triangle MPC, line segment AP divides the sides of the triangle MPC proportionally. And therefore, according to rule 21, that is the converse rule of rule 19, line segment LS, line segment AP, of course, must be the angle bisector of triangle MPC. And again, we should find out that because of the fact that in the right triangle MPC, line segment AP divides the size of this triangle MPC proportionally, that is to say, we know that B over A equals to MA over AC, therefore line segment AP must be the angle bisector of this triangle MPC according to rule 21. According to rule 21, rule 21 is the converse rule of rule 19. Repeat again, because of the fact that line segment AP divides the size of this triangle MPC proportionally, line segment AP must be the angle bisector of this triangle MPC according to rule 21. So, repeat quickly on rule 21. According to rule 21, here we have line segment AD. In triangle MPC we have line segment AD. And we know that line segment AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. So we know that line segment AD divides the sides of this triangle ABC proportionally. Therefore, line segment AD must be the angle bisector of this triangle ABC. Okay, line segment AD is the angle bisector of this triangle ABC. So we can implement rule 21 in our drawing. So as I mentioned before, line segment AP divides the size of this triangle MPC proportionally. That is to say, we know that B over A equals to MA over AC. Therefore, according to rule 21, line segment AP must be the angle bisector of this triangle MPC. Okay. So, if line segment AP is the angle bisector of triangle MPC, this means that line segment AP divides angle MPC into two halves. So, line segment AP divides angle MPC into two halves, because it is the angle bisector of triangle MPC, according to rule 21. Divides angle MPC into two halves. Angle MPC equals to 90 degrees in size. Therefore, each half of angle MPC equals to 90 degrees over 2, that is 45 degrees. This is the first half of angle MPC, equals to 45 degrees in its size. This is the second half of angle MPC. The second half is angle APC, is equals to X, is equals to 45 degrees in its size. So if we found out that the angle that we are looking for in this question, that is angle APC, is equals to X. Angle APC is equal to angle X is equal to 45 degrees in its size. So this is the answer to the first question. Repeat again that rule 19, that is also defined as angle bisector theorem, is the converse rule of rule 21. This is rule 19, that is also defined as angle bisector theorem. According to rule 19, if AD is the angle bisector of triangle ABC, it divides the size of this triangle ABC proportionally. The converse rule of rule 19 is rule 21. According to rule 21, if AD divides the sides of this triangle ABC proportionally, then AD must be the angle bisector of triangle ABC. Therefore, rule 21 is the converse rule of rule 19. We'll finish with the first question. In the next step, I present you the second question, and we'll solve the second question of this lecture. The second question, our task is to find out the length of this line segment CD is equal to x. So we have to find out the length of line segment x is equal to CD. In the drawing, we have a semicircle. This is point O, this is the center of this semicircle. This is line segment OE, this is equal to 5 units in its length. This is line segment EB, this is equal to 4 units in its length. In addition, we know that those two angles are both right angles. We know that also that CQ equals to PQ equals to QE. So if we define the length of PQ as A, then the length of CQ and the length of QE must be also equal to A because they are equal to each other according to what is given as the question. So, in the next step, we will join point C and P together by a straight line. By joining point C and P, we create the right triangle CPQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. So in the right triangle CPQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule to dimension. We also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in triangle CPQ must be equal to 180 degrees. Which angles we have in the right triangle CPQ? We have alpha plus 90 degrees. In total must be equal to 180 degrees. So it is now the right triangle CPQ the sum of the angles must be equal to 180 degrees. That is to say 2 alpha plus 90 degrees. In total, the sum of those two angles must be equal to 180 degrees. And again, in the right triangle CPQ, the sum of the triangles must be equal to 180 degrees. So alpha plus 90 degrees must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divide this equation by 2, and finally get that the missing angle alpha is equal to 90 degrees over 2, that is 45 degrees. So actually, found out that those angles are both equal to alpha, therefore each of them is equal to 45 degrees in its size. So write it down. is given us the question that CE is a straight line. So if we focus on the upper side of the straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is the right angle plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we join points P and D together by a straight line. This is triangle PCQ. Triangle PCQ is simultaneously an associated triangle and also a right angle. Why? It is an associated triangle because CQ equals to QP. And in general, you know that if a triangle is simultaneously an associated triangle and also a right angle, it will always have the same three angles. One angle is 90 degrees and the other two angles is 45 degrees each of them. This is the right triangle PQE. The right triangle PQE is also an associated triangle because of the fact that those two sides are equal to each other. Therefore, those two missing angles must be equal to 45 degrees each of them. This is true in an associated triangle that is also right angles. In the next step, we will do a construction, that is to say, we will complete this semicircle to a circle. So completed the semicircle to a circle. In the next step, we'll extend side CE by a straight line until it touches the circle. And we'll define the touching point of the extended side C with this circle. This point is point M. Likewise, we will extend CO, side CO by side line until it touches the circle. We'll extend side PE by side line until it touches the circle. And we'll define the touching point of the extended side PE with this circle. This point is point N. In the next step, we join point C and N together by side line. Likewise, we join points M and N together by side line. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees inside, therefore this missing angle must be also equal to 45 degrees inside, according to the rule that vertex angles are equal to each other. This is periangle CPN. Periangle CPN equals to 45 degrees plus 45 degrees is 90 degrees. So this is a right angle. Periangle CPN. Periangle CPN subset on code CN. Again, periangle CPN subset on code CN. Therefore, we can implement here all 5. Specifically all 5. According to rule 5, any periangle that is equal to 90 degrees inside must subset on the diameter of the circle. In the drawing, we have a circle. This is periangle MAN. We know that periangle MAN is equal to 90 degrees inside. And therefore, according to this rule, rule 5, periangle MAN must subset on the diameter of the circle. Indeed, periangle MAN subset on code MN, that is the diameter of the circle. So according to this rule, rule 5, any periangle is equal to 90 degrees inside must subset on the diameter of the circle. So we can actually implement rule 5 in our drawing. Right, because in our drawing, this is periangle CPN, is equal to 90 degrees inside, and therefore periangle CPN must subset on the diameter of the circle. Periangle CPN subset on code CN, and therefore according to rule 5, code CN must be the diameter of the circle. In the next step, we will implement the converse rule of rule 5, that is rule 7, on this periangle CMN. This is periangle CMN, the subset of the diameter of the circle. Therefore, according to rule 7, periangle CMN must be equal to 90 degrees in size. So repeat quickly rule 7. Rule 7 is the converse rule of rule 5. According to rule 7, if a periangle subset on the diameter of the circle, then it is equal to 90 degrees in size. The drawing we have a circle. This is periangle ACB, and we know that periangle ACB subset on the diameter of the circle, that is AB. Because of the fact that periangle ACB subset on the diameter of the circle, it must be equal to 90 degrees in size. So according to rule 7, any periangle that subset on the diameter of the circle must be equal to 90 degrees in size. So as I mentioned before, you can implement rule 7 in the periangle this peripherical CMN. Peripherical CMN subset of the diameter of the second, therefore it must be equal to 90 degrees inside according to rule 7. Repeat again that rule 7 is the converse rule of rule 5. Why? Because according to rule 5, if a peripherical is equal to 90 degrees inside, then it must subtend on the diameter of the second. The converse rule of rule 5 is rule 7. According to rule 7, if we know that the peripherical subtend on the diameter of the second, then it must be equal to 90 degrees inside. This is peripherical ACB. You know that peripherical ACB subtend on the diameter of the second, therefore it must be equal to 90 degrees inside. What is the radius of the circle? But before that, this is the small right angle EMN. In the small right angle EMN, this angle equals to 45 degrees inside. This is the right angle. Therefore, this first missing angle must be equal to 45 degrees inside, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this first missing angle must be equal to 45 degrees inside. What is the radius of this circle? Actually, the radius of a circle is defined as a line segment that starts from the center of the circle and ends on the point on the circle itself. When again, the radius of any circle is a line segment that starts from the center of the circle and ends on a point that is located on the circle itself. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of the circle. OB in total equals to OE, that is 5, plus EB, that is 4. So in total OB equals to 5 plus 4, that is 9. The radius of this circle equals to 9 units in itself. Therefore, the radius OB equals to 9, the radius OA also equals to 9. Likewise, the radius OC also equals to 9 units in its length. In the next step, we calculate the area of this triangle COE. Repeat again. We calculate the area of this green triangle, triangle COE. What is the area of this green triangle COE? Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of the green triangle COE must be equal to the base of the triangle times the height of the base over 2. The height of the base must create 90 degrees with the base or with the extended base. So therefore, the area of this green triangle COE will be equal to the base. We choose the base as CO. The height to the base must create 90 degrees with the extended base, with the base or with the extended base. CO is the base, therefore the extended base is Cn. So the height to the base must create 90 degrees with Cn, the extended base Cn. So from point D, we will do perpendicular on Cn. So this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point E and Cn. This point is point G. We define the length of EG as h. EG is equals to h, definitely creates 90 degrees with the extended base Cn. Therefore, h is the height to the base, is the height to the extended base CO. So now we should find out that the height for the entire CO is h over 2. So the entire CO equals to the base CO times the height h over 2. CO is the radius of this circle, is equals to 9. So in total we should find out that the area of the green triangle COE equals to 9h over 2 square units in size. Likewise, we calculate the area of this lower triangle OEN according to the symbol. That says that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of the lower triangle OEN is equal to the base of the triangle times the height to the base over 2. We choose the base of this lower triangle OEN as ON. Times the height to the base. The height to the base ON must create 90 degrees with the base. Therefore, h is the height to the base ON because it creates 90 degrees with the base ON. Those triangles are both right angles. So h is the height to the base ON over 2. So in total we should find out that the area of the lower triangle ON equals to ON times h over 2. ON is the radius of the circle, equals to 9. ON is the radius of the circle, equals to 9. The radius of the circle equals to 9. So we substitute ON by 9. 9h over 2. So in total we should find out that the area of the lower triangle OEN is also equal to 9h over 2, exactly like the area of the triangle COE. This is also equal to 9h over 2. Therefore, the areas of those two triangles are equal to each other. So I did not actually found out that the area of the triangle COE is equal to the area of the lower triangle OEN. And again, we should find out that the area of the green triangle COE equals to the area of the lower triangle OEN. In the next step, we find out the area of this big triangle CEN. What is the area of this big triangle CEN? Actually, we know that the area of the big triangle CN must be equal to the sum of the areas of the two components that this consists of. The first component that the big triangle CN consists of is the green triangle COE. So the area of the first component is the area of this green triangle COE. Plus the area of the second component that triangle CN consists of. The second component is triangle ON. So it is plus the area of the second component, that is to say, this is the area of the lower triangle ON. So then we should found out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the lower triangle ON. But we already found out that the area of the lower triangle ON equals to the area of the green triangle COE. So we can substitute the area of triangle ON by the area of triangle COE. This is the question. If I get that the area of the big triangle CN total is equals to the area of the green triangle COE plus the area of the green triangle COE. They are equal to each other. The area of triangle ON equals to the area of triangle COE. So we substitute the area of triangle ON by the area of triangle COE. So in total we should find out that the area of the big triangle CEN equals to the area of the green triangle COE plus the area of the green triangle COE. That is to say, it is equals to 2 times the area of the green triangle COE. So the area of the green triangle CEN is twice as large. The area of the big triangle CN is twice as large as the area of the green triangle COE. Here we divide this equation by 2 and we get that the area of the green triangle COE is half of the area of the big triangle CEN. In the next step, we calculate the area of this big triangle CEN according to the rule that says that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of the big triangle CEN is equal to the base of the triangle times the height or the height to the base over 2. We will choose the base of this big triangle CEN as CE. And the height to the base must create 90 degrees with the extended base. CE is the base, therefore the extended base is CM. Again, CE is the base, therefore the extended base is CM. And M definitely creates 90 degrees with CM. Therefore, NM is the height to the base. To the base or the extended base doesn't matter. Over 2. So in total we should find out that the area of the big triangle CN equals to the base CE times the height, that is NM over 2. The next step we focus on this small right triangle EMN. This small right triangle EMN, we have the rule that says that in front of equal angles in the triangle there are equal sides. So this small triangle EMN, in front of those two equal sides, in front of those two equal angles, we have those two sides that must be also equal to each other in the angles according to the rule that I mentioned. So if we define the length of this side EM as B, then the left side Mn must be also equal to B because they are equal to each other according to the rules that I mentioned. So the area of the green triangle the area of the big triangle CEN in total it is equal to the base CE. C equals to CQ, that is A, plus QE, that is also A. So in total C equals to A plus A, that is 2A. C is 2A times Mn, NM. Mn or Nm equals to B, according to what we have already found out, divided by 2. So in total we found out that the area of the big triangle CN equals to 2AB over 2. Here we have 2 in the numerator, 2 in the denominator, so 2 will get cancelled, and we left only with AB, A times B. So in total we found out that the area of the big triangle CEN is equal to A times B square root in size. The area of this big triangle CEN is equal to A times B square root in size. And we already found out that the area of the green triangle COE equals to the area of triangle CN over 2. It is half the area of the big triangle CN. So it is now. We already found out that the area of the green triangle COE is equal to the area of the big triangle CEN over 2. It's half the area of the big triangle CEN. But we just right now found out that the area of the big triangle CN is AB, so we substitute the area of the big triangle CEN by AB divided by 2. So in total we found out that the area of the green triangle COB equals to AB over 2 square root in size. So write it down. We found out that the area of the green small triangle COE is equal to AB over 2 square root in size. So in total we found out that the area of the big triangle CN is A times B, and the area of the small triangle COE equals to AB over 2. It's half of the area of the big triangle CN. In the next step, we will implement rule 65 in our drawing. Rule 65 is about two chords that intersect with each other inside the circle. So repeat quickly rule 65. According to rule 65, first of all, rule 65 is true in any circle. This is a circle that could be any circle. So in any circle, if chord AB intersects with chord CD at point O, the intersection point of chord AB with chord CD occurs at point O. So in this drawing, the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 65 in our drawing. Why? Because in our drawing, this is chord AB that intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. The intersection point between chord AB and chord CM occurs at this point E. So actually all the requirements of rule 65 are satisfied, and therefore we can implement here rule 65. So at the end we should found out that in our drawing, chord AB intersects with chord CM at point E. Therefore, according to rule 65, the following equation is true. AE times EB equals to CE times EM. Again, AE times EB equals to CE times EM. So write it down. AE times EM Again, AE times EB is AE times EB. Equals to CE times EM. And again, according to rule 65, although the following equation is true in our drawing, AE times EB equals to CE times EM. AE in total equals to AO, that is the radius of the circle, equals to 9, plus OE, that is 5, according to what is given as the question. So in total, A equals to 9 plus 5, that is 14. A equals to 14. Times EB. EB equals to 4 units in itself, according to what is given as the question. And is equals to CE times EM. CE equals to CQ, that is A, plus QE, that is also A. So in total, C equals to A plus 8, that is 2A. Times EM. EM equals to B units in itself, according to our definition. EM equals to B. So in total, we should know that 14 times 4 equals to 2AB. 14 times 4 is 56, so 56 equals to 2AB. Here, we divide this equation by 2 and finally get that 2AB over 2 is AB equals to 56 over 2 is 28. So we found out that A times B equals to 28. Write it down. A times B equals to 28. We already found out that the area of the big triangle CN equals to A times B. So write it down. According to what we already found out, the area of the big triangle CN is equal to A times B squared in size. But we just found out that A times B equals to 28. So we can write it that A times B equals to 28. And from this equation, we have that the area of the big triangle CN equals to 28 squared in size. We only found out that the area of the great triangle CO equals to the area of the big triangle CN over 2. So write it down. The area of the great small triangle COE is equal to the area of the big triangle CN over 2. This is the half of the area of the big triangle CN. But the area of the CN is also 28, so we solve the area of the CN by 28, over 2. 28 over 2 is 14. Those two sides of the equation are equal to each other. So in total, we should found out that the area of the great small target COE equals to 14 squares in size. So it is now the area of the small great target COE equal to 14 squares in size. In the next step, we will calculate the area of this green triangle COE according to the rule that says that the area of a triangle equals to the base of the triangle times the height to the base over 2. So the area of the green triangle COE equal to the base of the triangle times the height to the base or the height to the extended base, doesn't matter, over 2. So the area of the green triangle COE equals to the base, we choose the base SEO, the height to the base must create 90 degrees with the extended base. The base is EO, the extended base is EA. So the height to the base must create 90 degrees with EA, the extended base. CD definitely creates 90 degrees with EA, because this is a right angle. Therefore the height to the extended base is CD. The height to the extended base is CD over 2. So in total we found out that the area of the green triangle CO equals to the base EO times the height to the extended base, that is CD over 2. According to what is given as the equation, OE or EO equals to 5 units in its length times CD. CD equals to X. X is the last segment that we are looking for in this question. So we substitute CD by X divided by 2. Those two sides of the equation are equal to each other. So in conclusion, we found out that the area of the green triangle COE equal to 5x over 2 squares in size. But we already found out that the area of the triangle CO equals to 14 squares in size. So can I write here that the area of the green triangle CO equals to 14 squares in size. Those two sides of the equation are equal to each other. That is to say, 14 equals to 5x over 2. So it is now 14 equals to 5x over 2. Here we multiply this equation by 2. If I get that 14 times 2 is 28 equals to 5x. Here we divide this equation by 5. And if I get that x, that is the last element that we are looking for, is equal to either 28 over 5 units in its length, in terms of numbers. 28 over 5 is 5.6 units in its length. So from that, I find that CD is equal to x. CD is equal to x. It is equal to either 28 over 5 units in its length, in terms of numbers. CD is equal to x is equal to 5.6 units in its length. So we finish to answer the second question. In the next step, I'll solve the next step. That is to say, repeat on the solution of the first question and then repeat on the solution of this second question. Our task in the first question is to find out the size of this angle APC is equal to x. So we have to find out the value of angle x. In the drawing, we have triangle ABC. This is angle ABC, this is equal to 15 degrees in size. This is angle ACB, this is equal to 30 degrees in size. We also know that BP equals to PC. So if we define the graph of BP, then PC must also equal to A because they are equal to each other according to what is given us the question. Then again, we should define BP, therefore PC must be also equal to A. The next step, we did a construction, that is to say, we extended side CA of this ABC by a straight line. Then we did another construction, that is to say, it's point B, we loop angle that equals to 15 degrees in size in the following way. BA is one leg of the angle, and the other leg of the angle created in such a way that it will create 90 degrees with the leg BA. So this angle equals to 15 degrees in size according to our construction. In the next step, we extended this leg by straight line until it touches the extended side CA. We define the touching point of the extended leg with the extended side CA. This point is point M. By doing this construction, we created the associated triangle, triangle BMC. My triangle BMC is an associated triangle because of the fact that those two angles are equal to each other. Each of them is equal to 30 degrees and therefore they are equal to each other. Because of the fact that triangle BMC is an associated triangle, we can implement here rule 20. So I pitch quickly rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is of course the base of this associated triangle, triangle ABC. According to this rule 20, the perpendicular AD to the base BC bisect the base BC. First of all, those two angles are both right angles because AD is the perpendicular to BC. According to this rule 20, the perpendicular AD to the base BC bisect the base BC. That is to say, divides the base BC into two halves. The first half is BD, and it is of course equal to the second half DC, and each half equals to BC over 2 because BC is bisected by the perpendicular AD. So in total, we found out that the perpendicular AD bisects the base BC into two halves. The first half is BD. It is also equal, it is of course equal to the second half DC. Each half equals to BC over 2 because BC is bisected by the perpendicular AD. So can you implement rule 20 in our drawing? I put in our drawing. This is the associated triangle BMC. BC is of course the base of this associated triangle, triangle BMC. According to rule 20, the perpendicular from point M to the base BC bisects the base BC. The perpendicular from point M must touch the base BC at point P, not in any other point. Why? Because of the fact that point P is the midpoint of BC. That is to say, at point P, the base BC has been bisected into two halves. The first half is BP, that's right. It's of course equal to the second half BC. This is also equal to A. In each half equals to BC over 2 because of the fact that BC is bisected. So this angle equals to 90 degrees, and this angle also equals to 90 degrees because MP is the perpendicular to BC. In the next step, we focus on this right triangle BMP. This right triangle BMP, it is very easy to see that sin 30 degrees equals to MP over MB. But again, the right triangle BMP, sin 30 degrees equals to MP over MB. We define the opponent MB as 2B, therefore sin 30 degrees equals to MP over 2B, because MB equals to 2B according to our definition. Sin 30 degrees is 1 half, so 1 half equals to MP over 2B. We multiply this equation by 2B, we find out that MP equals to 2B over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled, we have to live with B inside of the equation. So in total, we should find out that MP equals to B. So if we figure out MP to the base BC equals to B units in itself. So in conclusion, we can say that if MB equals to 2B, then MP must be equal to B. MP is twice as long as MP. Again, MB is twice as long as MP. In the next step, we focus on the big associated triangle BMP. This big associated triangle BMP, AB is the angle bisector of angle MBC. Why? Because AB divides angle bisector MB into two halves. Each half equals to 15 degrees in size. And because of the fact that AB is the angle bisector of the associated triangle MBC, we can implement here angle bisector theorem. It is also defined as rule 19. So repeat quickly on rule 19. According to rule 19, this is triangle ABC. It could be any triangle. AD is the angle bisector of triangle ABC. That is to say, bisect angle BAC into two halves. Each half equals to theta. Because of the fact that AD is the angle bisector of triangle ABC, angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. Repeat again, because of the fact that AD is the angle bisector of triangle ABC, angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. So we can actually implement rule 19. It is also defined as angle bisector theorem. Now, associated triangle BMC. So we found out that AB is the angle bisector of triangle ABC, of triangle associated triangle MBC. Therefore, according to rule 19, it is also defined as angle bisector theorem. Angle bisector AB divides the size of this associated triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Again, MB over BC equals to MA over AC. Repeat again. In the associated triangle MBC, line segment AB, because of the fact that AB is the angle bisector of the associated triangle MBC, actually, angle bisector AB divides the size of triangle MBC proportionally. That is to say, MB over BC equals to AM over AC. Repeat again, we know that AB is the angle bisector of triangle ABC. AB is the angle bisector of the triangle ABC. Therefore, according to angle bisector theorem, angle bisector AB divides the size of triangle ABC proportionally. That is to say, BM over MB over BC equals to MA over AC. Repeat again. We know that AB is the angle bisector of triangle MBC. Therefore, the angle bisector AB divides the size of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. According to angle bisector, MB over BC equals to MA over AC. MB is 2B, BC is A plus A, that is 2A, it equals to MA over AC. MB is 2B, BC is 2A, it equals to MA over AC. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. So in this side of the equation, we have to leave with B over A equals to MA over AC. we found out that according to angle bisector theorem, B over A equals to MA over AC. So again, B over A equals to MA over AC. In the next step, we focus on this right triangle, triangle MPC. In this right triangle MPC, line segment AP divides the sides of this triangle MPC proportionally. Why? Because B over A equals to MA over AC. Repeat again. If you focus on the right triangle MPC, it's very easy to see that line segment AP divides the sides of the right triangle MPC proportionally. That is to say, B over A equals to MA over AC. And therefore, according to the converse rule of angle bisector theorem, it is also defined as rule 21, line segment AP must be the angle bisector of triangle MPC. According to rule 21, it is also defined as the converse rule of angle bisector theorem. So according to rule 21, line segment AP is defined as angle bisector of triangle MPC. Bit quicker on rule 21. According to rule 21, in the moment we have triangle ABC. AD is the line segment. We don't know that it's angle bisector. We know not that it's a line segment. But we know that line segment AD divides the sides of this triangle ABC proportionally. That is to say, we know that BD over DC equals to AB over AC. We know that BD over DC equals to AB over AC. And therefore, according to this rule, rule 21, that is the converse rule of angle bisector theorem, line segment AD must be the angle bisector of this triangle ABC. AD is the angle bisector of triangle ABC, that is to say, it divides angle BAC into two halves, each half equals to theta. So we can implement rule 21 in our drawing. Why? Because in our drawing, in this triangle MPC, AP line segment AP divides the sides of this triangle MPC proportionally. That is to say, we know that B over A equals to MA over AC. Therefore, according to rule 21, that is the converse rule of angle bisector theorem, line segment AP must be the angle bisector of triangle MPC. If line segment AP is an angle bisector, it means that it divides angle MPC into two halves. Angle MPC equals to 90 degrees. Therefore, line segment AP, that is angle bisector, divides this angle that is 90 degrees into two halves. Each half equals to 90 degrees over 2, that is 45 degrees. The second half MPA, angle MPA equals to 45 degrees. This is the first half. The second half, this angle APC, is also defined as angle X, also equals to 45 degrees, and inside, according to the converse rule of angle bisector theorem, it is also defined as rule 21. So if you found out that the angle that we are looking for in this question is angle APC, that is also defined as angle X equals to 45 degrees and inside. Repeat again that rule 19, that is also defined as angle bisector theorem, is the converse rule of rule 21. Why? Rule 19 is the converse rule of rule 21, because according to rule 19, this is triangle ABC that could be any triangle. According to rule 19, if we know that AD is angle bisector of this triangle ABC, then angle bisector AD divides the sides of this triangle ABC proportionally. The converse rule of angle bisector theorem is rule 21. This triangle ABC, we don't know that AD is angle bisector. This last just the line segment. But we know that line segment AD divides the size of this triangle ABC proportionally. That is to say, we know that BD over DC equals to AB over AC. And therefore, because of the fact that AD, line segment AD divides the size of this triangle proportionally, line segment AD must be the angle bisector of triangle ABC. So here we know that line segment AD is the angle bisector of this triangle, and therefore it divides the size of this triangle proportionally. In the converse rule, we don't know that AD is the angle bisector, but we know that line segment AD divides the size of this triangle ABC proportionally, therefore line segment AD must be the angle bisector of triangle ABC. So rule 21 is the converse rule of rule 19. So we finish with the first question. We finish to repeat on the first question. In the next step, I repeat on the solution of the second question. The second question, our task is to find out the length of line segment CD is equals to X. So we have to find out the length of line segment X is equals to CD. In the drawing, we have a semicircle. Point O is the center of this semicircle. Line segment OE equals to 5 units in itself. Line segment EB equals to 4 units in itself. This letter is letter B. So line segment EB equals to 4 units in itself. We also know that those two angles are both right angles. We also know that PQ equals to CQ equals to QE. So if we define PQ as said, then CQ and QE must be also equal to A because they are equal to each other. All those three line segments are equal to each other. Okay, again, CQ equals to PQ equals to QE equals to A. In the next step, we join points P and C together by a straight line. By joining points P and C, we created the right triangle CQP. In this right triangle CQP, we have the rule that says that in front of equal sides in the triangle, there are equal angles. So the right triangle CPQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned. The sum of the angles in any triangle is equal to 180 degrees, so the sum of the angles triangle CPQ must be equal to 180 degrees. Which angles we have in the right triangle CPQ? We have alpha plus alpha, that is 1, alpha plus 9 degrees, in total must be equal to 180 degrees. So the right triangle PCQ, 2 alpha plus 9 degrees equals to 180 degrees. Here we subtracted 90 degrees from this equation. When we found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divided this equation by 2 and finally found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. It's given us a question that CE is a straight line. So if we focus on the upper side of the straight line CE at point Q here, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is right angle plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in size. In the next step, we join points P and D together by a straight line. This triangle CPQ is a right angle, and it is also an associated triangle because of the fact that those two sides are equal to each other. So we can say in general that if a triangle is simultaneously associated triangle and also right angles, it will always have the same three angles. One angle will be equal to 90 degrees, and the other two angles must be equal to 45 degrees each of them. It is true in any right triangle that is also an associated triangle. And because of the fact that triangle PQO is simultaneously a right angle and also a isosceles triangle because of the fact that those two sides are equal to each other. Those one angle is the right angle, the other two angles must be equal to 45 degrees each of them. It is true in any right angle, there is also an associated triangle. In the next step, we completed this semicircle to a circle. Then we extended side PE by side line until it touches the circle. We define the touching point of the extended side PE with this circle. This point is point N. Likewise, the extended side CE by side line until it touches the circle. We define the touching point of the extended side CE with this circle. This point is point M. In the next step, we join points C and N together by side line. We join points M and N together by side line. In this so here we have those two angles are defined as vertex angles, when we know that vertex angles are equal to each other. But this angle equals to 45 degrees inside, therefore this missing angle must be also equal to 45 degrees inside. According to the rule that vertex angles are equal to each other. This is peripheral angle CPN. Peripheral angle CPN. This is peripheral angle CPN. This equals to 45 degrees plus 45 degrees is 90 degrees. That is to say it is a right angle. Peripheral angle CPN subtend on chord CN. That is so we know that peripheral angle CPN is a right angle and it's subtend on this chord called CN. Therefore we can implement here rule 5. So repeat quickly rule 5. According to rule 5, any peripheral angle equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing, we have a circle, and we know that peripheral angle MAN equals to 90 degrees inside. Therefore, according to this rule 5, peripheral angle MAN, that is the right angle, must subtend on the diameter of the circle. And indeed, MN is the diameter of the circle. So according to rule 5, any peripheral angle equals to 90 degrees inside, like this peripheral angle, must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. In our drawing, as already mentioned before, this is peripheral angle CPN. This is equal to 90 degrees inside. Therefore, peripheral angle CPN must subtend on the diameter of the circle. Peripheral angle CPN subtend on chord CN. Therefore, chord CN must be the diameter of the circle according to rule 5. The next step, we implemented the converse rule of rule 5. That is rule 7. This peripheral angle CMN. Peripheral angle CMN. This is peripheral angle CMN. That subtend on the diameter of the circle. Subtend on CN, that is the diameter of the circle, and therefore it must be equal to 90 degrees inside according to rule 7. Repeat again. Rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it must be equal to 90 degrees in its size. This is peripheral angle ACN. We know that peripheral angle ACN subtend on the diameter of the circle. AB is the diameter of the circle, therefore peripheral angle ACN must be equal to 90 degrees in its size. We can implement rule 7. Now drawing, so I mentioned before. This is peripheral angle CMN that subtend on chord CN, that is the diameter of the circle, therefore according to rule 7, must be equal to 90 degrees in its size. So in this triangle EMN, this angle equals to 45 degrees inside, this angle equals to 90 degrees, and therefore this first missing must be equal to 45 degrees in its size, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Repeat again that rule 5 is the converse rule of rule 7. According to rule 5, if a peripheral angle equals to 90 degrees inside, then it must subtend on the diameter of the circle. But according to the converse rule 7, if we know that peripheral angle subset of the diameter of the second, then it must be equal to 90 degrees in size. Again, that rule 7 is the converse rule of rule 5. What is the radius of this circle? The radius of any circle starts from the center of the circle and ends at any point on the circle itself. OB is the radius of the circle. Why? Because of the fact that it starts from point O, that is the center of the circle, and ends at point B, that is the point on the circle itself. So this is exactly the definition of radius. Therefore, OB is the radius of the circle. The value for B is OE plus EB. OE is 5, EB is 4. Therefore, OB in total equals to 5 plus 4, that is 9. So we found out that the radius of this circle equals to 9 units in itself. Therefore, the radius OC equals to 9, the radius ON also equals to 9, and so the radius OC equals to 9, and the radius ON equals to 9, and the radius OA also equals to 9. The next step, we calculated the area of this rectangle COE. The area of the rectangle COE equals to the base of the triangle times the height over 2. We choose the base of this rectangle COE as CO times the height. The height to the base must create 90 degrees with the extended base. The base is CO, the extended base is CN. So the height to the base must create 90 degrees with CN. From point E, we draw perpendicular on CN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So EG is the height to the base because of the fact that it's creates 90 degrees with the extended base CN. We define EG as H, so the height to the base, so the extended base CN is H. So the base of triangle COE is CO according to our choice, and H is the height to the extended base CO, that is H. So in total, we should found out that the area of the triangle CO equals to CO times H over 2. CO is the radius of the circle, that is equal to 9, so it is 9 times H over 2. So in total, we should found out that the area of the triangle CO equals to 9 H over 2 square units in size. Likewise, we calculated the area of this triangle OEN. According to the same formula, that the area of any triangle equals to the base of the triangle times the height of the base over 2. We choose the base of this triangle OEN as OE. The height of the base must create 90 degrees with the base. EG is equals to H, definitely creates 90 degrees with the base ON. So the height is H. So we found out that the area of the lower triangle ON equals to the base, that is NO times the height H over 2. ON is the radius of the circle, that is equals to 9. So we substitute ON by 9, so it is in total the area of the lower triangle ON equals to 9 H over 2 square units in size. But the area of the great triangle OE also equals to 9 H over 2. Therefore, we derive that the area of the great triangle COE equals to the area of the lower triangle OEN. Again, we found out in total that the area of the great triangle COE equals to the area of the lower triangle OEN. Next step, we calculated, we found out the area of this big triangle CN. What is the area of this big triangle CN? It is very easy to say that the area of the big triangle CN must be equal to the sum of the areas of those two components that it consists of. So the area of the big triangle CEN equals to the area of the first component that it consists of, that is actually the area of this triangle COE, plus the area of the second component that it consists of, that is the area of the lower triangle ON. So in total, the area of the big triangle CN equals to the area of the great triangle COE plus the area of the lower triangle ON. But we already found out that the area of the gain triangle COE equals to the area of the lower triangle ON. So we can substitute the area of the lower triangle ON by the area of the gain triangle COE because they are equal to each other. We did it, and so we found out that the area of the big triangle CN equals to the area of the gain triangle COE plus the area of the gain triangle COE. That is actually 2 times the area of the gain triangle COE. Read again. The area of the big triangle CN equals to 2 times the area of the gain triangle COE. We divided this equation by 2 and finally found out that the area of the gain triangle COE equals to the area of the big triangle CN over 2. The area of the gain triangle COE is half of the area of the big triangle CN. In the next step, we calculated the area of this big triangle CN according to the rule that says that the area of any triangle equals to the base of the triangle times the height of the base over 2. Here again, the area of the big triangle CN equals to the base of the triangle times the height of the base over 2. We choose the base of this big triangle CN as CE. The height to the base must get 90 degrees with the extended base. CE is the base, the extended base is CM. So the height to the base must get 90 degrees with the extended base CM. NM definitely creates 90 degrees with CM. So therefore the height to the base is MN. So we found out that the area of the big triangle CN equals to the height CE times the base CE times the height to the extended base CE, that is MN over 2. CE equals to A plus A, that is 2A times MN. What is the rule of MN? We have the rule that says that in front of equal angles in the triangle, there are equal sides. So repeat again, in front of equal angles in the triangle, there are equal sides. So in this small right triangle EMN, in front of those 2 equal angles, we have those 2 sides that must be also equal to each other and their lengths. So we define the length of EM as B, then MN must be also equal to B according to the rules I mentioned. So in total, we found out that MN equals to B. So we substitute CE by 2A and MN by B divided by 2. So in total, the area of the big triangle CN equals to 2AB over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled, and we left only with A times B. So in total, we actually found out that the area of the big triangle CN equals to A times B squared in size. But we already found out that the area of the big triangle CN equals to the area of the big triangle CN over 2. So I copied this equation here. And we just found out that the area of the big triangle CN equals to A times C. So substitute the area of the great triangle CN by AB are equal to each other over 2. So in total, we actually found out that the area of the great triangle COE equals to A times B over 2 squared in size. In the next step, we implemented Rule 65 in our drawing. A bit quicker on Rule 65. According to Rule 65, first of all, Rule 65 is true in any circle. So this circle could be any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement Rule 65 in our drawing. Why? Because of the fact that in our drawing, this is called AB. Intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. Point E is the intersection point of chord AB with chord CM. Repeat again. Chord AB in our drawing, chord AB intersects with chord CM at point E. So all the requirements of Rule 65 are satisfied, and therefore we can implement here Rule 65. According to Rule 65, the following equation is true. AE times EB equals to CE times EM. Again, AE times EB equals to CE times EM. According to Rule 65, the following equation is true. AE times EB equals to CE times EM. AE equals to AO, that is the radius, equal to 9, plus OE, that is 5, according to what is the equation. Total A equals to 9 plus 5, that is 14. Read again. A equals to 14 times EB. EB equals to 4. EB equals to 4, so in total on this side of the equation we have 14 times 4 equals to CE. CE equals to A plus 8, it is 2A times EM. EM equals to B. Read again. CE equals to 2A and EM equals to B. So 14 times 4 equals to 2AB. 14 times 4 is 56, so 56 equals to 2AB. Here we divided the equation by 2 and we found out that AB equals to 56 over 2 is 28. And again, we found out that A times B equals to 28. But we only found out that they of the beta LCN equals to AB. So according to this equation here, they of the beta LCN equals to A times B. We just right now found out that AB equals to 28. So we can write it that AB equals to 28. And from this equation, those two sides of the equation are equal to each other. That is to say, the area of the big triangle CN equals to 28 squares in size. We only found out that the area of the green triangle CN equals to AB over 2. So could the area of the green triangle CN or equals to the area of the big triangle CN over 2. So could this equation here. The area of the green triangle CN or equals to the area of the big triangle CN over 2. The area of the big triangle CN is 28. CN is 28 over 2. 28 over 2 is 14. Those two sides of the equation are equal to each other. So in total we should found out that the area of the green triangle COE equals to 14 squares in size. The next step we calculated the area of this green triangle COE according to the rule that says that the area of green triangle equals to the base of the triangle times the height of the base over 2. The area of the green triangle COE equals to the base of the triangle times the height of the base over 2. We choose the base of this green triangle COE, that's EO, and the height to the base must get 90 degrees with the extended base. OE is the base, the extended base is EA. So the height to the base must create 90 degrees with EA. CD definitely creates 90 degrees with EA because this is a right angle. So the height to the extended base is CD. So total we found out that the green triangle O equals to the base EO. EO is the base according to our choice, and the height to the base is CD. CD creates 90 degrees with the extended base EA. Therefore it is the height to the base. So in total we found out that the area of the green triangle CO equals to the base EO times the height CD over 2. According to what is given as a question, OE equals to 5, CD equals to X, that is line time that we are looking for in this question. And again, EO equals to 5, CD equals to X over 2. Those two sides of the equation are equal to each other. So in total, we should found out that the area of the green triangle COE equals to 5x over 2 squares in size. But we already found out that the area of the green triangle COE equals to 14 squares in size. So we can write it that with this equation here. So the area of the green triangle COE equals to 14 squares in size. Those two sides of the equation are equal to each other. That is to say 14 equals to 5x over 2. If we multiply this equation by 2, we can find out that 5x equals to 14 times 2 is 28. So 5x equals to 28. If we divide this equation by 5, and we found out that x equals to 28 over 5. In terms of numbers, it is 5.6 units. So we found out that line side CD is equals to x. It is equals to either 28 over 5 units in its term, or in terms of numbers, it is equals to 5.6 units in its term. Okay, thank you very much.